Building technology is constantly evolving, but as we seemingly solve one problem, we typically create another. When things are advancing this quickly, it is difficult to find the time required to properly evaluate these systems as well as their impact on a building and its occupants. Today we'd like to discuss the specification of heat and energy recovery ventilation. HRVs and ERVs are quickly becoming more popular in the building community, as they have the ability to resolve a number of issues as well as enhancing indoor air quality. The T.H. Chan School at Harvard recently conducted a study relating to the cognition levels of people working indoors. They conclusively found that thermal comfort, continuous fresh air ventilation, and better lighting conditions resulted in cognitive improvement on the order of 26%. Changes in the upcoming code cycle and Title 24 credits are beginning to reward the addition of HRVs. We wanted to take a quick look back at the recent past to better understand where we are presently. It is well known that older structures tend to leak more air. They are so leaky, in fact, that they typically provide a limited supply of fresh air. This was acceptable when energy was cheap and seemingly plentiful, but population expansion and other factors have led to higher prices and energy conservation efforts. Energy efficiency measures have become an essential aspect of modern construction. We've clearly made advances in energy conservation, but these tighter, better insulated buildings have sadly had a detrimental effect on indoor air quality. Outdoor air quality is typically 3 to 5 times better than the air indoors, and tighter buildings have allowed pollutants to concentrate to even higher levels. It was initially thought that continuous exhaust-only ventilation, such as a bathroom fan, could mitigate the issue. But in a tight house, where does this air come from? Attics, crawl spaces, interstitial spaces, chimney flues? It would be tough to characterize any of these as fresh air, and on top of that, it's not conditioned. So much for energy efficiency. Not to beat a dead horse, but exhaust-only ventilation also results in negative pressure, which pulls uncontrolled moisture into interstitial spaces. I think we can all agree that this was and continues to be a poorly thought out strategy. Heat and energy recovery ventilators are one way to intelligently address the indoor air quality issue, and they provide numerous other benefits that improve occupant health and comfort. These systems are typically balanced, bringing in continuous filtered fresh air from outside, while harvesting energy from stale air that is being simultaneously expelled. Incoming and outgoing air streams pass through a heat exchanger to recover the thermal energy from the outgoing stream of air. The conserved energy results in energy savings and thermal comfort. Significant Title 24 credits are now being given in California for HRVs and ERVs based upon unit performance. On the surface, evaluating these units seems straightforward. Watt draw, cubic feet per minute, and energy efficiency specifications are entered into a software program and credits are given. One issue to consider is that a manufacturer might list CFM for air delivery while listing energy efficiency at a different CFM level and watt draw at a minimal CFM level. Realistic performance should be evaluated at standard operating speed, as this will provide a more accurate idea of what a unit will actually deliver. Speaking of energy ratings, one of the most critical is energy efficiency. In other words, what percentage of energy in the outgoing stream of air is conserved and imparted to the incoming stream? This chart shows the impact of efficiency on the temperature of incoming air. The difference between 60% and 90% efficiency is essentially apples and oranges. After reviewing these numbers, you may wonder why units rating even lower than 60% are being utilized to satisfy indoor air quality requirements. If a unit is at 60% efficiency, on a 40-degree day, fresh air is returned to the home at 58 degrees. How many BTUs will it take and how long will the conditioning system need to run to readjust to 70 degrees? If a unit with 90% efficiency was installed in the same condition, it would supply the air at 67 degrees. Units that are substantially below 90% efficiency are negating a significant amount of the energy conservation gained from air sealing and insulation measures. Credits are given for air recirculation, which leads to gradual degradation of indoor air quality. This should not be a substitute for high efficiency, and crediting recirculation is questionable at best. One of the most frequent questions relates to the difference between HRVs and ERVs. Which one should we specify and why? HRVs are designed to recover heat, and in humid conditions they can also condense excess moisture, although it is important to note that HRVs are not true dehumidifiers and should not be relied upon for dehumidification. ERVs have a different core than an HRV. This core allows for water vapor to be exchanged. These units act to stabilize interior moisture in both humid and dry climates to create more favorable conditions within the ventilated area. ERVs tend to be slightly less efficient when it comes to thermal recovery, but moderating humidity within the home is generally well worth the trade-off. Now that we've discussed heat recovery units and their associated performance levels, let's delve into delivery systems. Delivery systems have as much to do with performance and outcomes as the units themselves. Many HVAC professionals seem to have a hard time understanding the differences between ducting requirements for high velocity, high volume systems like forced air heating and low velocity, low volume systems like HRVs. When they field engineered ducting systems for HRVs, the results can be extremely disappointing. Static in a low flow system must be minimized in order for performance to be optimized. Blending systems with one set of ducting is generally a poor idea, as volume and velocity vary so greatly between the two systems. An engineered system of components is critical in achieving consistent and predictable results. Systems should either be supplied by the manufacturer of the HRV, or an MEP should be hired to properly design systems based upon volume and velocity in order to deliver ventilation in line with unit performance specifications. Delivery components in non-conditioned areas should also be insulated to maintain efficiency levels. With the increased use of solid engineered beams and other components in today's construction, running of plumbing, ducting, electrical, data cables, and fire sprinklers is becoming a more significant challenge. Conflicts and limitations in routing can be averted to some degree with the use of web trusses. These are widely available with wood or metal webbing that will facilitate routing of all systems within the home. The minimal additional expense can mitigate a myriad of issues with compromised framing and frustrated subcontractors. It is certainly worthy of consideration. The primary thing to consider when specifying HRV and ERV systems relates to project goals. What should a client expect from these systems? If the purpose of the HRV is to optimize energy recovery and provide fresh filtered air, then that is what it should do. Lower efficiency, lower cost HRVs are creating a negative experience for those buying and installing these inexpensive units. If you couple a poorly performing unit with a poorly designed delivery system, the results will speak for themselves. As design professionals, we may not be able to stop this from happening, but we should not be perpetuating it. Low price and high performance sounds like a great solution, but as with anything, if it seems too good to be true, it likely is. The specification process for heat recovery systems should include careful consideration of project needs matched to unit capabilities. Delivery system requirements should also be taken into account. The quote request process should include specific direction regarding locations of heat recovery units, exterior supply and exhaust vents, and other delivery components. There will always be some minor field engineering due to routing challenges, but pre-planning can minimize these so that results can be optimized and confusion on site can be minimized. A site meeting with the subcontractor and the product representative is typically a good idea, especially if this is their first experience in dealing with HRVs. The design process for Zehnder ventilation systems is fairly straightforward. David Green is our Southwest Regional Zehnder Sales Manager, and he's always happy to discuss any questions and concerns. We realize that all projects and clients are different. These systems are highly customizable to include typical or enhanced airflows, as well as standard or finer levels of filtration. When it comes to the design quote process, the best results are a product of thoughtful communication up front. The Zehnder Request a Quote and Request a Commissioning portals are a great tool to upload information, including plan docs. You can quickly enter specifics regarding the project, client needs, and any other concerns so that we can accurately address these. We utilize the information that you provide to create a free quote and system design. We also offer one free design revision. This should be used to finely tune the system based upon project specifics. Thank you for your interest in heat recovery ventilation systems. We hope this presentation was helpful, and please feel free to contact us with any questions. We look forward to working with you in the future.